Okay, in this video, I'm going to go over verifying your answers. Basically, how to check if the function you found actually fulfills the equation. Now, it would be nice to be able to have time to do this on your AP exam. You probably won't, but it's still worth mentioning. If you do have to verify, here's how you would do it. There are questions that are multiple choice type that actually don't want you to solve them. They just want you to basically get the answer by verifying which one of the equations would work. Once again, due to all this coronavirus stuff, the new test that they're giving you says it doesn't have any multiple choice. So I don't know if you'll see any questions of that type, though they could incorporate a check into free answer questions. So I just want you to be prepared. So the way you're going to verify, I'm going to verify the two problems that I did before. Now, if you watched the other video, we already came up with the answer to this, and we came up to with the answer to this. So I'm going to then show you me verifying that the answers I got are in fact correct. All right, so let's look at this first problem. I have just the solution to it and then the check. So if you want to see how it's solved, watch the other video. But I'm assuming you've done that and you already know how I got the solution. So I have the original differential equation, dy dx equals negative 4xy squared. And that initial condition that if you plug in 0, you get 1. That gave me this solution. So the solution was y equals 1 over 2x squared plus 1. Now, if I want to verify if this truly is the answer, because this is supposed to be what solves that differential equation, check it like you would a normal equation. Basically, I'm going to figure out what the derivative of y is and see if it fulfills the equation. So basically, I'm claiming that this equation, this function, has the property that when I plug it in, it'll be equal to this. So to verify it, I'm actually getting the derivative of this. Now, if I want the derivative of this expression, it's a quotient, and I'll have to use the quotient rule. So this section is me getting what dy dx is. Dy dx of this function, well, derivative of the top is 0, leave the bottom alone, subtract the top, derivative of the bottom. Now, the derivative of the bottom is going to be 4x plus 0, so I just put 4x. After you do the top part of the quotient rule, remember it's over the bottom squared. So after simplification, this function's derivative is negative 4x over 2x squared plus 1 all squared. Now, to do the verification part is, my claim is that this thing fulfills this equation, meaning its derivative should go in here and equal the other side. So I'm actually going to take this derivative and replace it with this to do the verification. So that's what I did over here. This derivative is going in for that, and I'm now going to verify that these two are the same. Now, they don't look the same at first because the left has all x's in it and the right has a y in it. But now, if I make the replacement, if I take that y squared, well, I know what y is supposed to be. If this function really fulfills it, this function should be what I'm squaring to get that y squared. So I actually took that function and squared it. So I replaced the y with what I think it should be, 1 over 2x squared plus 1. See if it works. Well, I'll square that thing. Squaring the fraction means square the top and square the bottom. So if I square the top, I get 1. If I square the bottom, I get that 2x squared plus 1 squared that I'm hoping to get. And if I multiply these together, put that negative 4x over 1, you can just multiply those together, and there it is. It's verified. So the function that I found originally really does fulfill this equation. It makes both sides equal. It's the one function that has this property. All right, and if I want to fully verify it, not only does it fit the differential equation, but it should also be true that if I plug in 0, I get 1. I didn't show that part, but that's easy to do. If I plug in 0 to this, I get 2 times 0 squared plus 1. That works out as 1, and 1 over 1 is 1. So if I plug in 0, I do get out 1. So it fits this condition, and it also fit the derivative condition where it is verified. So this is verifying the first one. Here's the second one. This one had the y prime. So this was the original differential equation. This was my claimed solution. It was a family of solutions, so I'm leaving that C blank, but that's the claimed solution. So same thing. If I want to verify this, first I want to see, well, what is the derivative of this? I did the quotient rule. I think the only little hiccup is to make sure that when you do the derivative of 1 plus cx, because basically I did derivative of the top, the bottom, derivative, or top left alone, and derivative of the bottom, c is being treated as a number, so derivative of 1 plus cx is just c. Then I went through and just simplified it, so I got that the derivative of that function is 1 over the quantity 1 plus cx squared. Now I want to verify, since that's my function and that's its derivative, does it fulfill the equation? We'll plug the derivative in to that equation and see if the other side works out. And if you follow the work, you'll see I separated the y squared and the x squared into y squared and 1 over x squared. But once I replace that y squared with what I think the answer should be, it does verify itself. So I do get that that family of functions works in there. Now, I don't have a specific answer because I said that c could be any number, but so long as if I made that c a number, it would still work in the original equation because it doesn't really matter what the number is. All right, so this is how you can verify the equations. It's basically analogous to when you solve an algebra problem and you figure out the answer is a number, you put the number in to see if it actually works. Here, you actually find a function for your answer, and you can actually plug the function and its derivative in to see if it really fits the differential equation. All right, so this is on, once again, verifying your answers. It's unlikely you'll have time to do this, but the skill may be tested in another way, which, like I said, when we get some of their practice problems, we'll see if they do any of this. Most of the time I've seen this tested multiple choice, but I don't want to leave it to chance. All right. This is the third video. The last video will have the solutions to the problems I asked you to try on your own.